Okay, so what I'm going to do is I'm going to press on. I want to talk about a few more techniques as we wrap the chapter up. So we were talking about linear dielectric material. So we started discussion of linearity in terms of polarization. This is, of course, polarization per unit volume. This is proportional to the electric field. The more the electric field, the more polarization we have. For linear materials, not all materials are linear, and even if they're linear, they're only linear to a certain range of magnitude of the electric field. And we brought out a factor of permittivity of free space, and then we had a proportionality constant. What was the name of this constant? Can't recall all of a sudden. Susceptibility. Yeah, correct. Thank you. Okay. And then we could define a displacement vector. It turned out to be the reason being we had polarization charge density to be okay. Because of this substitution, we could write this, and as a result, we would have the free charges, not the bound charges. The boundness was absorbed by the susceptibility term. And then we had various boundary conditions. Okay. Now for linear dielectric materials, inside the bulk, you cannot talk about, so when I say inside, I mean truly inside, not in the on the boundary. Okay, so this is a linear dielectric material, and then what will you have? You would have that. Let's see. I can do. Suppose rho free is equal to 0. You have a linear dielectric material, and you have a way to turn on electric fields. And we want to see what happens inside the linear dielectric material. We have seen it for several different cases. We have seen it for a conductor, where the potential where the electric field just vanishes. We have seen it for a uniformly polarized material. Okay, there the electric field diminishes. Now it is a linear dielectric material. So let's write some of the equations. Things these might this inside region might satisfy. You will see it satisfies Laplace's equation as well. So in particular, I would have d perpendicular above minus d perpendicular below is equal to rho free. In our case, this is 0, which means epsilon above, E perpendicular above.
Is it sigma or rho?
This is the boundary condition, so it is sigma.
So, okay.
Yeah. This is the up versus down. So imagine this, some sort of a sigma f, so d up and d below.
Okay. Yeah.
The perpendicular component. Yeah. So, but look at this d, and so we have another one. This can be rewritten as where epsilon, the permittivity, not of free space, but of the linear dielectric, is defined like so. So I can just translate this minus epsilon below E perpendicular below is equal to 0. Correct. That's why I wrote above and below. Yeah.
So it does change?
The permittivity would change. If this is a dielectric and this is not a dielectric, or if you have two different dielectrics,
Right.
you can have one dielectric surrounding another dielectric. Okay, fine. Now, what happens to this? See, this means inside a region, okay? Divergence of D equals divergence of epsilon E is equal to typically this one, but we're considering this case, so we would get 0, or divergence of E is equal to 0. So then, well, curl of E is always 0. This itself implies that E can be written as negative the gradient of a potential. So divergence of E equals 0, that implies del squared V equals 0. Or this is nothing more than Laplace's equation. So over here, I have del squared V equals 0. Outside, there are no charges. In this whole problem, there are no charges. So this is also del squared V equals 0. So all the spherical harmonics can be done. But it might be, things might get a little easier if we can write this in terms of the potential. And let's do that. Well, let's do that for a specific problem. Now, I mean this for this to be a perfect sphere. I could mean, for example, this could be any solid chunk of a linear dielectric. And what is important to us is the fact that if you don't have any free charges, so I'm focusing on this, if you don't have any free charges, Laplace's equation is satisfied, and this is the boundary condition that we need. So I will hang on to that part and do the specific example that I want to do. From the textbook, which is problem. So again, please make sure you follow the argument. This is example 4.7. So what you have here is a linear dielectric. And then you're immersing the linear dielectric in an external electric field. So there is, very far away, there is, I should write E equals E0 Z hat. You're just putting this dielectric material, a linear dielectric material, in a bath of external electric field. Obviously, what's going to happen is there might be some bound charges coming in, and it might distort the picture. Let's see what they are. But the point is, inside, del squared V equals 0, and outside, del squared V equals 0, because there are no free charges. I've just shown that that's the case. Okay. So we know the inside, so V inside. We've done this before. It's spherical harmonics. It's AL, R to the L, PL, cosine theta. We just want to make sure boundary conditions are satisfied. And then V outside, remember it has that BL over R to the L plus 1. The summation is over L equals 0 to infinity. If I pick this inside, as R goes to 0, this remains finite. If I pick this outside, as R goes to infinity, this remains finite. I couldn't put this in the outside region, but that is almost the case, except there is a field outside. It should give me this. So I would put a correction here. Can you tell me a potential whose negative gradient would give me E0? It is E, or negative, good, negative E naught Z. And, oh, yeah, so this continues, huh? That's what it is. Let me write that a little more clearly. What I wrote before was just the normal case when things are bounded. I would have minus E naught Z plus BL over R to the L plus 1 PL cosine theta. And thankfully, I can write this is minus E naught. Z is nothing more than R cosine theta. Well, I don't like cosine theta. I like P1 cosine theta. Now, what are the boundary conditions? Well, for one thing, potentials are continuous. Evaluated at R equals R. Yeah? And the second thing is this one. E above. Oh, wait a minute. Can I write it like this? Look, E above. What I'm going to make that E out. Above is going to be out, and then over here, outside, it's vacuum. So I can write it as E0, E perp out, minus E, not 0, E perp in is equal to 0. Are we good?
That's the surface condition, right?
Those are the boundary conditions we must meet. You're right, so we should technically write this as R equals R. R equals R. These are the two conditions that we must satisfy. First, let us satisfy the equality. Not that finding the electric field perpendicular is going to be that hard. Okay? So what does that mean? It would mean AL, or sorry, rather summation. AL R to the L PL cosine theta equals, I'll tell you why I'm cheating. In particular, you might wonder why I'm, oops. When L is not equal to 0. This is, sorry, not equal to 1. When L is, so let me simplify this. This means L, for every L, this has to be true. Or AL RL is equal to B to the R, L plus 1, BL. Again, this is when L is not equal to 1. Let me write the L equals 1. That'll make your life a little easier. And A1R, this is P1, is equal to E0R P1 plus B1 over R squared. Isn't that true? The P1 contribution comes from both terms of minus.
So that first line, we're setting them equal because of the boundary at R, they are equal.
The potentials are equal. So what I'm doing is I'm going to set them term by term equal so that I can cancel off the PLs. How can I do that? I just do an integration with another PL prime, and everything goes away but one of the terms. So that's how I get this. But when L is equal to 1, there's a P1 here. So the equality of potential, I'm going to erase that side. I'm going to write it as AL RL is equal to BL over R L plus 1 when L not equal to 1 and A1 R equals minus E0 R plus B1 R squared. Please confirm. Ask me a question, how I expect, most important, you should know how I went from here to here. How did I just set the coefficients of this to be equal? If the sum is equal, why am I setting the coefficients equal? I mean, there could be other ways. They could be, maybe the first two terms here could be equal to the sum of third and fifth term over there. But I'm saying, no. I'm saying this implies coefficient by coefficient they're equal. How can I conclude that? Perhaps, but I'm actually using the orthogonality relationship. I can take this and multiply it with PL prime cosine theta and PL prime cosine theta on that side, and then I can do sine theta, d theta, and integral. Then everything dies except for when L equals L prime. And I would get 2 over 2L prime plus 1 on both sides. They cancel. And this equation will remain with L primes. Then I replace L primes with L.
So still, why did we never include the E0R P1 cosine theta in that?
This is when L is not equal to 1.
P1 doesn't depend on L, right? That first term.
That's L
is
equals
just
1.
P1.
That's L equals 1.
Yeah, that is cosine theta.
Okay, well, tell you what, I'm just going to do it. Sometimes it's, and it's not a bad idea for me to do it. So, what is this? I'm going to write small because at some point we're going to run out of space. Or P. You know P1 is P1 cosine theta, right? Plus BL over R to the L plus 1 PL. So then what I'm going to do is the following. I'm going to do well, if I do it on this side, what must I do? This side. I'm going to pick, well, okay, fine. I won't pick anything. What happens on this side? What is this? PL prime sine theta d theta 0 2. This is equal to 0 if L is not equal to L prime. It's equal to 2 over 2 L prime plus 1 if L is equal to. Happy? I can stop using green. So over here, what am I going to get? I'm going to get AL prime RL prime 2 over 2 L prime plus 1. Yeah? Over here, I'm going to get minus E0 R 2 over 2 L prime plus 1. I'm going to write, you may or may not have seen this notation, but let me explain. Delta L prime plus, I'll explain that term. This means this is 0 if L is equal to, oh, sorry. This is 0 if L prime is not equal to 1. If L prime is equal to 1, it is this. Correct? Because it's only P1. If this is P17, if I pick L to be 17, I get 0 here. If I pick L prime to be 0, I get 0. If I pick L prime to be 3, I get 0. But if I get L prime to be 1, I don't get 0. Yeah? Well, naturally, I can get rid of this. It's the same thing. Correct? You don't seem to be happy.
Well, I guess you would have the delta to say, or to see.
Hold on. I need to, we have not. Delta Mn is equal to 0 if M not equal to N, equal to 1 if M equal to. That's what it is. But I mean, it's, I cancel something which is non-zero. It's 2 over 2 L prime plus 1. It can never be 0. So I can do division by, division on both sides. Then, L prime yeah? So let me do the unfriendly variable, L equals 1. I would get A1R minus E0R delta 1, 1, which is 1, plus B1 over R squared, L1 plus 1. When L is not equal to 1, it goes away. Yeah? Are we good? It is because of the orthogonality condition, I can say they have to agree term by term. If a vector is equal, how do I know each components must be equal? Because I can do a dot product with x hat, y hat, or z hat. If I do a dot product with x hat, only the x hat component gets picked up. And they have to be equal. Same thing, I think I mentioned this before. You can think of this as a dimension, nth direction. The dot product is replaced by this integration. This is an infinite dimensional space, vector space. Such spaces are called Hilbert spaces. Okay, now I have to balance this condition. So obviously, I'm going to set this equal to that. So epsilon naught minus dv out. Are we good with that? What is the perpendicular component? The radial component. And what's the radial component of the gradient? Just partial with respect to r. R equals r should be equal to minus epsilon. No longer epsilon naught. dv in dr, r equals r.
Are we taking radially outward to be the negative? Or?
No, no, no. E is negative the gradient.
Oh, yeah.
Yep. So it should actually go in here.
All right.
So let's do this. Let me clarify. E out is equal to r hat dot E. R hat dot negative gradient of V. So that is negative r hat dot gradient of V. When you look at the formula for this, this is dv dr for gradient in spherical coordinate system. That's how I got this expression. So minus epsilon naught. This is an easier one to do. L, AL, I'm cheating, L minus 1, PL is equal to minus epsilon E0 P1 minus BL L plus 1 R to the, what is it? L plus 2 PL, and oh, I shouldn't do this, delta 1L. I've done several things, none of which I like so much. First of all, I took the derivative with respect to r, and then I replaced it with big R. So when I take the derivative with respect to little r, I get L times r to the L minus 1. But then I'm evaluating it at this step. I tried to save a line by doing this, but I think the explanation takes longer. Right? I took the derivative with respect to little r, and then replace the little r with capital
But why
R.
did you do it with the inside?
What do you mean?
Like, isn't that supposed to be the VL?
Right, this is the outside. A is the outside. Ooh,
Came from there, right?
no. Oh, right. Inside, this is what? This is inside, correct?
Yeah, that's inside.
And so this is outside.
All right, that was easy for you.
Thank you. Thank you. But let's, so obviously this breaks down to two cases. L equals 1 and L is not equal to 1. When L is not equal to 1, I get L, AL, R to the L minus 1 equal to epsilon. Yeah, I'm going to cancel the minus sign. Get epsilon naught. But there's a minus over here. I would get BL, L plus 1, R to the L plus 2 when L is not equal to 1. Then when L is equal to 1, I get epsilon A1 P1 is equal to E0 minus B1 2 R cubed. So at this point, I want to make sure I'm not making any mistakes, and I want to check with the book. So let me check this condition. This is correct. A1R minus R squared, correct. Then I get oh, sorry, not P1. P1's cancel. I would get, it's better to put minus here. Just dropping. Oh, this is, let me make sure. Minus is 0, minus 2b over r cubed, correct? L, AL, r to the minus 1, minus BL. Yep, everything seems kosher. I'm sorry?
Where's our electric field and
Oh, sorry. This is also, sorry, you were saying?
So, you know, we have capital E naught, P1, the delta 1L. Where is that?
Oh. Correct. That should go. Yeah? So we have, these are the two conditions that must be met. I will leave, I'll do one part of the algebra. I'll leave the trivial part of the algebra for you. When L is not equal to 1, AL equals 0 equals BL. Meaning, if you set this to be equal to that, you won't get any non-zero compatible solutions. Meaning, you replace BL with whatever you get here on this side, and you won't get anything compatible. The only thing compatible will be from this term. So now let's solve for that. So when L is equal write out the two conditions we need. And then we'll do the algebra. Have A1R is equal to minus E0R plus B1 over R squared. My goal is to solve for A1 is equal to minus epsilon naught E0 minus 2, again epsilon naught B1 over R cubed. These are the two equations that I have to satisfy. I need to find the values for A1 and B1. These are simultaneous equations. So what I'll do, so these are the original equations, I won't mess with it. Let me rewrite this. B1 R squared. And then I'm going to do this. Epsilon A1 R, I'm multiplying by R. I get minus epsilon naught E0 R. And I would get what? Minus 2 epsilon B1 over R squared. And then what do I need to do? Multiply this guy by epsilon. And then add them up. When I add them up, what do I get? So I would get A1R, this plus this. These two cancel away, and I would get what? Is equal to minus 2 epsilon naught E0 R. And then I get A1 minus epsilon naught 2 epsilon naught E0 I can simplify this. This is minus 2 epsilon. I feel like I could have made so many mistakes, but I'm good with that too. Nope, that's not what is supposed to happen at all. It's supposed to be a 3. I'm getting the minus is correct, this is correct, this is supposed to be a 3.
Oh, well, we couldn't cancel those because it's 2 epsilon naught B1 over R squared. So it's multiplied by 2. And then negative makes 3.
So we have 2 here. So then what happens? That doesn't help either. So these two go away. And this becomes a negative 3, correct? But this becomes a 2. sure the equations are correct. Let's solve for, because I don't want A1R equals B1 over R squared, and then epsilon, okay, A1 minus E0 minus 2B1 over R cubed. They're in fact correct. So let's make sure 2 epsilon naught, 2 epsilon naught, 2 epsilon naught. And this one we're just writing it, what are we doing? Multiplying by R, correct? Okay. So then I would get A1R, I would get 2 epsilon naught plus epsilon is equal to what? Minus 3 epsilon naught E0 R. Yeah? I'm not entirely happy with that answer. I could be.
Which solving for A1, right?
Yeah. I'm going to divide every term by epsilon naught. Then R. So I have A1, 2 plus R. It is correct. Remember? The dielectric constant. Yeah, and that is in fact this fact. And then, once we get A1, life is easy. We can go solve for B1. So before I erase, I'm not going to worry so much about minus 3 E0 over 2 plus the dielectric constant. And then you can go back and put in B1. With interest in time, it turns out to be ER. Okay, again, that is just algebra. But most importantly, the potential inside is what? V inside. It is A1, R1, I'm sorry, R1 cosine theta. So that is 3 E0 over 2 plus R cosine theta, or even 3 E0 over 2 plus constant Z. So electric field inside, because I know how to take the Cartesian negative gradient, is in the Z hat direction.
Do we drop a negative over?
No. This is the inside.
Yeah.
Oh, A1 had a negative. Yep, you're correct. Yep, and let me make sure. 3, 0. Yep, 2 plus R. So as a result, what's going to happen is the inside electric field we just calculated is uniform. But the outside electric field gets distorted. And then far away, it's still, you can write V out and then find the electric field just by taking the gradient. It's not too bad because only 2 terms remain. It's easy to. So you can imagine, time's up, you can imagine even